You can just go up here to the top, and you can go to design and quick layout. And that's my quick layout. It's my favorite one. You know, it's in the chart title, all this stuff. I think I'll show this again real quick. Got all these options, got so many cool things, it's so nice.
Gary! I was just looking for the sports channel, Gary.
Hey everybody, a little bit of SpongeBob right there. So we're all trying to figure out how to get the points. It shows me who's got points. Oh my gosh. Wait, what? Wait, why is it working now? Why does that work right there? Nicholas did it. Nicholas gets, wait, can I add points? Let me add points to Nicholas right here. Nicholas figured it out, and I have no idea why that would work. So, why is it working now? I thought we were all doing this. Let me try adding points to Nicholas. I swear we're all typing the same thing. Oh, everyone's looking at their points now. Yes, everyone wants to know their points. It's working. Why does it work? I swear we were all typing that. Okay, so I go points, add. See, it's so much work. And then Nicholas, let me copy paste your name. We're going to try to give Nicholas 1,000 points right here. So we're going to try to give Nicholas 1,000 points. Points, add Nicholas 1,000. Okay, there. So let's try this. We've ruined the economy now. We've given Nicholas 1,000 points. So let's see if this is working. Why would Streamlabs... And you should have more points than that, because I thought I set it higher for all these live streams. You should have more than like... oh. Is it running all the commands now? It looks like it's like catching up. Well, we're going to try to figure this out. Oh no, Kyle, you have 0 points. So everyone's looking at their points. We're going to keep trying to figure this out. I'm so sorry. It can't be because you're not a mod. That can't be it. I'm making you mod, Kyle. But we're trying to figure this out. So obviously this system is not perfectly working right now. So I'm not going to judge extra credit by this. But my goal is that I start to move the extra credit over to this. So here's how the points are supposed to work. It's supposed to work the longer you watch live. So if you're actually like watching live, and then if you make comments are worth like 20 points. Oh yeah, you still have all your points that we've given you, like when I give you points. But then, so David, let's make you mod here too. These points won't actually be used to calculate anything because I don't have the system working properly. I'm still trying to feel like, okay, and but this is going forward in the future because I can actually track who's watching the videos and who's interacting. So I can say like, you know, when you give answers, it's worth this many points. So people know if they're watching the video and interacting, they get points, and then these points are at the end of the semester. And then you know how like right now it's kind of like, oh, I'll have to calculate it all on the sheet, and it's kind of the honor system. It actually, you know, is really great. It moves us away from the honor system. Not that it makes, I think it's a capital P. Maybe it's to do a capital P. Still keep tracking your extra credit. Keep tracking the extra credit, and I'm going to keep trying to work on this in the background. And for some reason, the Ethernet I'm using, my Ethernet cord, I should change the cord. I just got two 20-foot cords, and I'm going all the way between. But still we have... I know, Streamlabs is, man. So I need to work with the cloud bot. If anyone has any info on this, maybe we could do like a Zoom session and I'll start working on this. These are just, one Mew buck is worth 1/1000th of a regular point right now. They have no conversion rate. The economy can't handle Mew bucks right now. Good to see you, Matthew. So I'm working on this, trying to create some new things. This is what I'm doing in the background with my spare time, is trying to make it even better. So imagine now, like, it's not that it doesn't work this way now. Just deal with my hand right there. But in the future, if you're watching the video and if you're interacting, you get the points. So that I can track it literally. It'll track from me how much people are commenting, how much they're interacting, how long they're watching, because it can tell if you're actually like interacting on the video. It just kind of tracks the chat and then gives points. So it should work. We're back, baby. You got it. It should work with points. Oh, is that David? Does that work? If you guys find new commands you can write into Streamlabs, give it a shot. We'll get teaching here in a half second. We got some news though. We got office hours. He tells me my Mew bucks. I wonder if I can make it mine. Let me try fixing my Mew bucks here. So there we go. Let's give it. Oof! I ruined the economy. There we go. Let's see how many I have now. See if it worked. Will it show me them? It's so weird. I guess it's like talking to Streamlabs and it takes a moment. So, or I broke it. I totally. Oh, there. Oh, wow. Look at all my Mewbucks. That's cool. So I can actually give people big points still, and it should work. Let's do one last try of this right here. It should work with the following. I should be able to put in, and hopefully I'm the only one who can do this. Hopefully, like mods can't do it. Points, remove. So that's the example right there, and then we go stat 201. See, it's so much to type at UTK, and then we'll put that right there. So yeah, that's thank you so much. I might be on that one right now. I'm on the How to Streamlabs one. So and then we look at my points now, and then we'll get serious here. So let me see if I just removed a whole bunch of points for myself. No, I didn't remove the points yet. So, or yeah, no, I didn't remove the points. Okay, well, so I'll figure out more on how to do this and the commands and all this. Well, why do you use YouTube? I like it a lot more. It's just the way it's set up, like the way I can do the streaming on this. I feel like it's a lot easier to interact with you guys, and I like it better. Also, you know, Zoom has been having issues lately, so I have none of those issues on YouTube. Yeah, I'm not the biggest. I mean, Zoom's all right. So, yeah, I think it's easier to chat this way too. I can instantaneously see what everyone's saying. There's no like, I can use my professional mics and stuff. I can probably use that with Zoom too, but I like this. This is my personal favorite way of doing it. So, oh yeah, maybe there's a whole many things you could do. It's so cool. Okay, let's see. We'll get serious here, and send me some stuff, Andrew. I know you kind of love this stuff too, but send me info on this. Send me that link too. I'll find it in the chat. Good stuff. Good to see you, Will. Let's add you as a mod right here. The stream, yeah, me too. It's just easy to. It's just streaming, and I think on Tuesday we will have we will start doing the whatchamacallit. I keep saying it. I keep teasing it. How about on Tuesday we do office hours on Maybe I should just do that only. What if I only do office hours on... If I only do office hours on... why can't I think of it? Twitch. There's one link. So you won't have to worry about videos. You can just come straight to Twitch, and I'll be streaming office hours on Twitch. What would you guys think about that? What if I only do office hours on Twitch, and then you don't have to worry about what video do I click on? You just go right to Twitch, and boom, you're on my channel, and I'm streaming to you. So that way you're not like, oh, what video is Brian on? What video is this? You come to the Twitch channel. I'm streaming on Twitch. How would that sound? That'd be great. I was just thinking about that right here. So I'll update the 201ers. I think that'd be really great too. So let's make that happen. So here's what we need to do. The Twitch, yeah, I got the Twitch channel. It's not up and going. If you guys want to start subbing to it. Let me find it, and then we'll start getting serious here. Where is it? Oh no. Wait, do I have it? I found it. I found it. We got a cool background and everything. It says we will be back soon. we've never broadcast. Okay, so we'll take all that right here. Send me the questions about the code. It's been busy. I've been replying to about 100 to 200 emails a day for Lab 7 out. The lab last week. Are you talking about the lab last week? Lab last week. That sounds weird. I like that, David. That's awesome, David, right there. Connected the N and the D on your name and said David instead. The lab last week, yes. The lab last week is going to be, sounds like Bob Law's firm, when I keep saying lab last week. If you guys know, some Arrested Development right there. So amazing show. I'm going to put this link in the chat, and then we're going to get serious right here. So it should be called Lab. And you guys can clip out. I'm afraid of what's going to get clipped on Twitch now. Oh no, I made every font smaller. Okay, so here you go, Kyle. It's in the chat now. And feel free, everyone, to put this. Tfue, I know. Yeah, that. Is he Fortnite still, or is he? What do they play? They play. What do those people play? I don't know. I don't know the games anymore. I'm too old. You're welcome, Kyle. Always glad to help. That's why I really like, I like the way we do this right here. I know people were asking earlier. He plays Fortnite, so there you go. Yeah, I guess, I don't know, like, one of these days I'll play Fortnite. We've got like a Stats 1 Minecraft server. I might start doing that this weekend. Apparently they've got it up. It's in creative mode, and that makes me a little bit sad. Club Penguin. You got to get on that iceberg and make it, and make it collapse. Fortnite is a dead game? Oh, really? What's the game now? What is the game now? Let's get one more minute, then we're gonna get serious. Okay. Flip the bird. Yeah, that's what it was. I watch a guy, Brutal Moose. He's really great. Brutal Moose, Ian is one of my favorite content creators when it comes to video games. Of course, like Cinemassacre, Angry Video Game Nerd, Pat the NES Punk, trying to think who else. Who else? Probably Brutal Moose has some of my favorite reviews. Do you know, I guess John might know Brutal Moose. Really great content right there. So can everyone lock in and focus on class, please? Yes. Well, let's get serious here. Okay. Is everyone ready to go? It is class time. Let's do this, David. You ready? Last lecture, we were talking about partition models and partition trees. So we had our fun. Time to get serious now. Partition models and partition trees and how the splitting of the trees work. We ended right with the complexity parameter. So when it comes to the complexity parameter, what does it do? I want to start seeing it in chat right now. It's time to get serious. What does the complexity parameter do? What does the complexity parameter do? Anyone have any ideas on what the complexity parameter does? Any ideas? What does it control for the tree? Remember, your final is going to be a lot of true falses, a lot of multiple choices. We have a meeting this Friday about setting it up. Controls how much the tree grows. Andrew gets it right there for 100,000 points. Aaron, sorry, Andrew is above you. Right there. How big it grows, how large the tree gets. So when you think about the complexity parameter right here, we have larger values of complexities lead to smaller trees. And why is this? I wish we could do a written test, because you're saying how much does the tree need to improve by? Now you can look right here. We've got the formulas written out. I think it's right here is one of the values for how we calculate CP. And this is saying how much of a change in the sums of squared error do we need? Now another question, I'm hitting you with all these questions. How does the, when we use sums of squared error, what kind of tree are we building? This is a very, very simple question. If it's sums of squared error, it means a certain thing about the tree. We know this, that if we're analyzing sums of squared error, we have to be doing this type of tree. We would know it instantaneously. It's like, oh, it's sums of squared error. That means this variable is this. So you got it right there, Caleb, for 100,000, Andrew and John and Will. It's quantitative. We know the y variable is quantitative. Sums of squared error means we're trying to predict the mean of a value. And we can see this throughout multiple examples on these slides, that this right here is a categorical tree because we have impurity. Impurity can be measured by two things. I'm hitting you with so many questions right now, 100,000 points. Impurity can be measured with two things. This is a review of last class. Remember, you get a cheat sheet for the test too. Impurity can be measured by two things. Gini coefficient is one of them for 100,000 points. John is right. The Gini coefficient, which we have formulas for, and entropy. Andrew is right. Gini coefficient and entropy are measures of impurity. What do you want impurity to be? Keep putting those answers in the chat. Remember, impurity is a bad thing. So you want impurity to be this. When you're measuring impurity, you want it to be 0. Kyle gets 100,000 right there. Lower is correct. I know. You're getting the points if you put it in here, Matthew. You keep getting the points. Matthew, 100,000 joining in. But you want impurity to be 0. This is you guys saying it in class to me right now and practicing that impurity is a bad thing. Just kind of makes sense, right? Joel, good to see you, 100,000 points. And Zach, 100,000 also. So remember, we do not want impurity. Now, here's a big concept on this slide. Every time you see a box on a slide, you have to be like, okay, let me know the big concepts here. What does this mean? This is telling us that there are tuning parameters. It might not say it completely, but there are tuning parameters, and there's two of them right here. One tuning parameter is how big we're going to let the tree grow. This is controlled by the complexity parameter. The complexity parameter controls how big does the tree grow. That is huge. The complexity parameter is controlled by how big does the tree grow. The second tuning parameter is how many is the min observations in each leaf. No, David, 100,000 points, David, and go down to the bottom and click live. At the bottom of the screen here, you'll see a button that says live. It'll be way over there. It'll be over there on the side, and you'll see a live button. You can also increase the quality, but click live, and you should be as like 2-3 seconds behind when I say things and with everyone else. Thank you, David, right there. David, it says it to 100,000 points. That'll catch you up to everyone right here. Okay, so we have two tuning parameters that we're focusing on. Min observations, which is the second one on the screen right here. Min observations, the refuse to split after too few individuals in a leaf, and also we have complexity parameter. Complexity parameter is the return we must receive to split the leaf. to split to split a leaf, and then it'll make more leaves below it. So, or partition to make more partitions. Nice job, David. Always glad to help. So what we see right here is if the complexity parameter is high, the tree is saying, okay, we have to get a big return to split, so it won't split. But if the complexity parameter is low, then the tree's gonna be like, oh, I can just split if I don't get a return at all. Figuring out this optimum value of complexity is data dependent. You can't just use one value of complexity, and this is what's so cool about predictive modeling. When you do predictive modeling, you don't make one model, you make a whole bunch of models, and we'll see this here in the notes. So here's the code. This is so key. Please, 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 that's going off the slide. Well, you can copy paste it. But please, please, please know what this code is doing. Let's take a look. We've got here that the train control, this is setting up the cross-validation, and we're going to store it into something called fit control. Method, CV, cross-validation. You can use boot or repeated CV. It would require more parameters. Number 5 is k-fold 5 validation. Class probs equals true means that we're tuning on accuracy. There's a two-factor summary. Once again, and I usually copy-paste these. I'm just being honest. I'll usually just copy-paste it because it's the same thing every time. But class probs means it's categorical and you're tuning on accuracy. And then there's two-factor summary, which means you're tuning on ROC, AUC. And then we have here the R part grid. Now this is key. This is what I was just talking about a moment ago. We have right here that we're making an expand grid, and I'm probably going to pull up R here in a second to show what this looks like. Let's go here, and these are probably some of my favorite questions to put on the test. They're so easy to write. Easy questions are the best for tests, like easy to write questions. So we're going to hop into our studio and make sure we know what this new type of code does. Let's hop right here and look at this expand grid, and what does it do? The expand grid literally just puts out the CP levels. Now, what you could do, now, I don't know if it's min-obs in this, but let's take a look. Let's go 25 and 1. That's going to be a way too big tree. I like my spaces. So it should work. This code should work. Can anyone tell me how many values will be in my expand grid now? For 1,000,000 points, who can tell me how many values will be in my expand grid now? This will tell you how expand grids work. As soon as you know the answer to this, for 1,000,000 points, as soon as you know how this works, you'll understand the expand grid, like what it's doing. Who knows for 1,000,000 points, how many values will be in my expand grid now? If you're quick, you could type it out. Who knows? I'll give everyone a moment to think about it. 20's in there right now. There's currently 20. 20 is incorrect. Remember, only one person gets the 1,000,000. Everyone else is getting 100,000 now for giving an answer. Will is right with 60. Will is right. Will is right. Nice job, Will. So the answer is 60, and let's explain why. So what it is, and so everyone else gets 100,000, great job, Will, is look at what it did. Our original expand grid was only tuning on the CP, so we get all the values of CP. This is just an equation, which don't worry about all the sequence stuff. It's literally just making a sequence of 20 numbers that lowers the CP, or actually it's going to increase it. Just, yeah, now there's a CP of 1 right here. No worries. Will was super quick. And so right here, we go and we look at the new expand grids. No. F in respect. F, I don't know, we were doing that earlier, and I don't know, all the memes. So good job, David. I'm throwing you another 100,000. So we got you caught up now. And what do you notice? Does everyone understand what's going on when you look at this? Here are the values of CP with min-obs 20. Here's the value of CP with min-obs 5. Here's the value of CPs with min-ob 1. But let's say we had another thing in here, like if we had random variable 3. I don't know what else we could tune on right now. We really can't. But if this value right here had 5 values, then what's going to happen to my expand grid now? So, how many values for another 1,000,000 points will be in my expand grid now? You'll know how it's working if you can tell me. And this is I love these test questions. They catch a lot of people, but once you know how it works, you're like, oh, nope, Will, you were quick, but nope, not 100. You have to use the previous answer to get this one. You have to think about the previous answer. And I'll start putting some notes in here. I'll see who gets it. No one's gotten it yet. Remember, there's like a 2-second delay here. So I'm putting some cheat answers in here. and you'll see how it's done. And Will got it. Will is correct. It is 300. So I think the comments will be fine on the end of this. And if you notice, it's just permutating all the values. So if you look at it right here, you get our original expand grid right here. And you see there's the 4s, there's the 5s. Does everyone see what's going on right here? That it's 20 times 3 times 5, and you get this exponential growth. Haha, that's a fun topic. And it just keeps growing the amount of values we'd look through to make our models more and more and more and more and more. Who thinks they understand what's going on here with the expand grid, that it makes all combinations? Connor, we were kind of talking about this via email. It makes all combinations of everything. That'd be awesome. So who thinks they understand what's going on here with the expand grid and how it permutates all the values and makes all combinations of everything in the expand grid? So it makes every single combination of everything in the expand grid. This is a big topic for today, how the expand grid works and how we can search for models and we can tune these. We can see which of these works the best. So if I were making if I were to make models from this, it would make 300 different models. Yep, you're just that's it, Kyle. Million points, Kyle. That's exactly a great note to take. The expand grid multiplies all the different values, not the values, but like if there's 20 different in the first and there's 3 in the second, and if there's 5 in the third, it multiplies all those values, and that's how many combinations there are. So the quickest way to do the math is 20 times 5, 100, 3 times 100, 300. So there are 300 different combinations of models we are making, or 300 different model combinations to make. If you keep adding lines, you would multiply them instead of values you just keep multiplying. Like if there's another random variable here, like if I make a random variable 4, now someone tell me, someone tell me now how many models I will make now. How many models for another million points? Last time for the million points. How many models will I be making now? 900. Saeed, you got the points. Great job. And it reached max print. But if you notice right here, we got 250 max print. How did it print 300 and then it reaches 250 max print? You're weird sometimes. So this is what's going on. 100,000, Jessica, David, and all the people answering. If you know what's going on right here, you understand the expand grid, which is going to be a key focal point. So we need to know that this is just making the combinations of models that we'll use and we're calling it our part grid because it's like what we're going to use for our partition grid. We've got right here the train. We got y tilde x comma data equals. Don't know what accent that was. And this is just classic. This is the formula format to say we're going to choose some y variable. And then we're going to have all the x variables in here because it's going to partition on its own. We're not going to tell it what to do. We're going to use the training data because this is predictive modeling. The method we're going to use is going to be part. So that's the third y tilde x comma data equals comma method equals. We've got the way the train control is set up. It's the fit control. That's a callback to there. And then we've got the tuning grid right here. And last but not least, which you can barely see off the screen, so sorry, is the preproc. The preproc is going to center and scale them so that way we really don't have things with undue influence. So it's going to center and scale everything. That turns everything into z-scores. Oh, Connor. Yeah, you're right. We should do that. I don't know. Here, let me do that real quick. Connor, 100,000 points to Connor right there. He's right. You can change the options on the max print. So options, and then it's an argument inside of here, max.print. There we go, equals 1,000. I'm not gonna go crazy. What? There we go. I have no idea what's going on. I thought I made it large enough. Oh, maybe it's like how many things it prints or not how many rows. Yeah, it might be number of observations. So we could test that out. I'm very interested in that. Yeah, it's how many observations it prints. It's not the number of rows. That's why. So it's number of observations, not number of rows. Because if you notice, at 300, it stopped at 75 because there's 4 rows. So at 300, it stopped at 75 because there are 4 rows right here. So 4 times 75. So that's what the max print controls. It's not how many rows, it's how many observations it'll print. Interesting. Learn something new every day. So we'll continue back right here. You can look at the results of how it's doing, and this is going to tell you which model you're going to use. So we're going to start looking at that here in just a moment. You need to know what your code is doing. I can't state that enough. One of the best compliments I got from this class was someone said, I've learned so much about these algorithms, but now I finally know what they do, because they had taken classes on this, and they were like, I've been computer science, nothing against computer science, but they're like, now I feel like I know what I'm actually doing and the point of this. So the point here is that we want to look at our model with the highest accuracy. Okay, that's kappa over there. I was like, what's going on? We've got the highest accuracy right here, and this is going to tell us the CP. So if you look at these right here, here's a tree that's close to the naive. It just depends on how you set up your tuning grid, because a CP of e to the negative 1 is 0.1. Hopefully I'm doing my math correctly. And then these would be smaller tuning trees. So these trees right here are, since they have a smaller CP, they're going to be bigger trees. Remember, smaller CP, bigger tree. CP is inverse to tree. Yep, you can pause it and then catch back up live. Yep, just hit the pause button at the bottom. So CPs are going to be related to the tree size, and you can do smaller CPs to get bigger trees. And remember, this is scientific notation. But also, I do want to point this out, that when you make your expand grid, and you will see it in the notes sometimes, it's good to know this, that when you do expand grid, you can make your tree list any way you want. So you could literally make a CP right here equals, and you could do, we usually let it compute it for us, but you could do this right here, and there's your expand grid of that, but there's nothing stopping you from, and I'm going to use a quick command right here. Do I know it? Is it R or is it reverse? Is it R? I think there's a function that just reverses a vector. No. Is it rev? It is rev. Yep, little tiny commands that, what I missed. It's just the numeric value. And here, I'll go back and look at that in here in a second, Kyle. If you notice right here with these values, the CP right here goes from what would be larger trees to a smaller tree, but here it goes from a smaller tree to a larger tree. Larger values of CP make smaller trees. They're inversely related. Smaller values of CP make larger trees. So whenever you see output, be very careful, because it just depends on how someone wrote their code. Here's the reason this is the highest accuracy. Be careful. That's the accuracy. This is the kappa statistic. I don't use kappa that much. I'll be against us putting it on the test. When you go to your boss and you talk about kappa, you'll have to explain what kappa is. But if you just talk about accuracy, it's way easier. You're like, here's how accurate the tree was. It was 62.3% accurate. So good to have you back. 62.3% accurate is better than trying to talk about kappa and being like, it's a 0.2272 kappa. And they're like, what does that mean? You're like, well, it relates to how the impure. Yeah, no. I just like to talk about accuracy because it makes more sense in the business world to say something like, it was this accurate in predicting the model or predicting the Y variable. So accuracy is something everyone understands. So rather than trying to teach the whole world what kappa means, we've got accuracy, and I think that works way better. So there you go. There you go. We've got the importance right here. These won't really go to interpretations, but it'll tell you basically which variables are going to be the most important in the tree. And this is actually going to be pretty interesting as we keep making models. Those are such crazy faces. So we have here, when pictures are highly coordinated and share redundant information. Yes. This is pretty awesome right here because we can see which variables are actually the most important, and maybe this could help a business person hone in on it. So when you think about the application of this stuff, which I always want us to be thinking about, this class is not just about writing code, it's application. You might try with your predictive model to then look at the relationship these variables have, which we can do. So we can make some really cool graphics coming up here that show us the relationship between these variables. So we have here partitioning the data. When making a new rule, the impurities are calculated only on those observations which are not missing a particular predictor, then adjusted to account for the fraction of missing observations. So we've got here the number stands for the number of missing values right here. Don't worry too much about this. I wouldn't worry too much about the slide. We will not have you, I don't plan on having you do this calculation by hand. So a surrogate variable is the one that is used in place of x when it is missing. To find a surrogate value of x, we must predict x using string tree with a single split. Don't worry too much about this. Not too much going on here. Let's continue on. Here are some examples of diabetes right here. So this shows us what's going on here with the tree. There we go. All these waiting. Look, our messages are redacted. I have no idea what's going on in the chat. So we've got right here the complexity parameter of the tree. This was the tree that was selected to have a certain complexity parameter right here. So we've got a decently growing tree, And we've got here pregnancy, the improved to the tree with how many observations are missing. And I don't really use this output that much. We'll start looking at the tree going on, but agree, there we go. And we have the surrogate splits down at the bottom, the primary splits. Cool. We're going to start getting to the big concepts today. Samples diabetes. Here we go, our surrogate variable importance. Don't worry too much. We won't do much on surrogate splits. I don't even think it's in the other slides. So example using one. Here we go, here we go, here we go. That's, I know, such a creepy emoji. Okay. Imagine a marketing team making a multiple logistic model or nearest neighbor for quality of wine. Let this fit this, estimate the generalization, and then use the train to find a vanilla partition model. Okay, awesome. I want everyone to notice something huge right here. We haven't done this much before, but right here with this code, we've got an expand grid also. I want someone to put in words for me what the expand grid is doing. I want someone in words to explain what that code is doing. It's setting something up for the train code you're about to see such that it does a certain thing, such that it tests a certain thing. Like, why would you write that code? What is the point of that? And I like maybe multiple choice questions like this, like, why would you write this code? Like, would it be that you want to run the k-nearest neighbor 10 times and see how it does 10 times? That could be an answer right there. That's like, you want to run k-nearest neighbor on 10 different subsets. You want to run k-nearest neighbors to pretty much, David, you got it for 100,000 right there. That's kind of it. Like, you're testing, you're right, where k is equal to the values 1 through 10. And so you're using k-nearest neighbors 1, k-nearest neighbors 2, k-nearest neighbors 3, k-nearest neighbors 4. And that's what an expand grid does, is it, David, why not 1 million? No one else answered yet, so I'm going to give you 1 million because you are the only person answering on that. So k-nearest neighbor 1:10 will run the models k-nearest neighbors 1, k-nearest neighbors 2, k-nearest neighbors 3, k-nearest neighbors 4. And then let's look at the code right here. This is going inside of the results of k-nearest neighbors. So it's going inside of the results and it's retrieving the row that has the best tuning to it. So it's going to find the one with the best accuracy, and that's the only one it's going to report. And interestingly enough, it's k-nearest neighbors 1, which people might think is overfit, but because you're having like everything vote basically on the area around them, but the k-nearest neighbors 1 is the one that worked best on the validation. So apparently k-nearest neighbors 1 is a pretty good idea. You never know. Everything is model dependent. But does everyone understand what's going on with this code? That is so key to what we're trying to do, is that you should understand that when we run the train function, it's y tilde x, comma, data equals, comma, method, and we're using k-nearest neighbors, and then we're going to do the train control, which we already set up. Where's our train control at? There it is. So we already set it up to be CV. We have to have class probs because it's categorical. Please take a huge note right now. If you are doing accuracy and predicting categorical variables, because it's accuracy, you have to have class probs. If you are doing ROC, you have to have two-factor summary, and those codes are in the notes. If you're trying to find them, can't find them, email me, but you have to use this. You can literally take this right here and copy-paste this to your assignment. I do it all the time when I'm writing this stuff out. I'm just like, let me grab that fit control, because it doesn't change. If you're using it with k-fold 5, boom, you got it right there. Here we see the train also being used for the generalized linear model. We're doing a center and scaling on both of these. I like this better. It's the way I more often write it. Can you say it one more time? Yes. When you are doing your fit control, you need to make sure you set it up properly. You need to make sure if it's categorical that you have class probs equals true. And there's some notes I can post for you guys also that shows you how to set up each fit control, but there are really 3 separate fit controls you can use. A fit control for quantitative, a fit control for categorical, which when you're setting it up, you're tuning on accuracy, and that's the one I currently have highlighted, and then a fit control for categorical when you're tuning on ROC. So your 3 fit controls you can use, or that we generally use in this class, are a fit control setup for quantitative, a fit control set up for categorical when you tune on accuracy, the one highlighted right here, and a fit control which has 1 extra argument in it set up to tune on ROC, which is going to be when we do it on a categorical variable. And it has the 2-factor summary equals, trying to think, it's 2-factor summary equals true, or 2-class summary equals true. Huge note. Yes. Thank you, David, right there. So keep taking those notes and put them in the comments. Someone already had a comment. 1,000,000 points for everyone who adds a comment below this video with a timestamp. If you timestamp something and don't use someone has already taken, but if you go back and find a timestamp and be like, this is where Brian explains fit control, this is where Brian explains CP, timestamp it, 1,000,000 points, and I'll try to add as many of them as I can to the comments, but 1,000,000 points for each timestamp, because I know a lot of people might use this to study, to hear just the part where I talk about CP again, just the part where I talk about this again, but give those timestamps, and that's awesome. I really appreciate that, and that's one of the things Zoom can't do. Okay, let's continue on. We'll stop bashing on Zoom. Let's continue on right here. We've got the k nearest neighbor 1 is what's the best model. Next slide. So here we go right here. We can see the complexity parameter right here. As we increase the complexity parameter, this is going to make our tree. Let's see, larger complexity means a smaller tree. So at this point, I think the tree might be the what? Can anyone tell me at that point it kind of flattens out? Would the tree be very large or very small? And the tree might be very close to this. Like, this is all conceptual stuff right now, because the complexity parameter is pretty high. And if the complexity parameter is pretty high, the tree is going to be pretty what? And it might be closer to this. Any ideas? And I think you might have to clarify that. If the complexity parameter is pretty high, the tree will be going towards this. It'll get very this, and it'll go towards this. The tree would be very small. Yep, 100,000 points, all his answer right there. It's both Aaron and Christian. Remember, if the complexity parameter is high, the tree gets small. So it's an inverse relationship between complexity parameter Ivy right there, 100,000 points. It's an inverse relationship between complexity parameter and size of tree. Larger complexity, smaller tree. And the tree is probably going towards the naive, which would have no splits. The naive model would just be the majority level. Once again, that's a review from last class. When it's a categorical tree, the naive model would be the majority level. And if this complexity parameter gets high enough, the tree will just not do any splits. If the tree does no splits, it's just all the data, and we would predict based on the majority level. So I think this tree at this point is probably going towards the naive model, if not obtaining the naive model. These are conceptual things you should think about when you see a graphic like this, that as the complexity parameter is going up, the tree's actually getting smaller. Complexity, high tree, small, yep, which would go towards David. Amazing job. Remember these timestamps. Yes, 1,000,000 points. I'll let you guys even get 2,000,000. Remember, the point economy is crazy right now. But when I give 1,000,000 points, that means I really want you to do that, because I know it'll help people out. So thank you very much. We've got right here our expand grid. That's where each of these dots are. Each of these dots are on where one of the expand grids is. So there's 20 dots total. You might wonder why it looks weird. It's because it's a sequence of 10 raised to this value. So you see something like 0.1, and then you just get the interesting values between and all this stuff right here. If you want to learn about math and statistics, you're in the right spot. Good to see you here, Leo. We're talking about making trees and all that fun stuff. So learn more about statistics. So we got right here that the best tree is going to be this one right here. Does everyone see why this is the best? But we do get some interesting stuff about this. Every tree, this is an amazing question for 100,000 points. Every tree that would be similar to this tree that we could technically pick would be within 1 what of this accuracy. So does everyone see this accuracy right here, which I'm going to highlight. I had a box for a second. Every tree that would be basically similar to this would be within 1 what of this accuracy. Like you should be like, boom, I know that. Every tree that's, yeah, Aaron right there, 100,000 points, you're right. The standard deviation is our uncertainty. So when you think about what standard deviation means, standard deviation is just uncertainty in an estimate. Yulia right there, 100,000, you guys are getting it. So, and Zach and Jessica. So every tree that is basically similar to it. And you do notice that maybe that tree, the one tree right here, is a pretty big jump. It has a CP of this. So when we actually make the tree, we could pick that one. But one standard deviation tells us, well, it's basically identical to it. That's something we should know pretty quickly. We did that a lot before spring break when we actually would see each other, that one tree is very similar. And here we see CPs going down. So these trees are getting bigger. If you notice how CPs are going down right here. So these trees are lower complexity, bigger tree. And we go right here and we can actually see all the trees within 1. So, you know, a decent test question with this right here. I keep trying to think of test questions. Like, I feel like Brian comes up with a test question right here. Is how many trees on the slide right now are identical to the best model? Do not include. So 1,000,000 points for this. I'm going to have to figure it out as we do it. So you can start taking guesses or figure it out. How many trees are virtually identical to the best model And I think, yeah, I think it, well, let's see. I'm going to start figuring out by hand right here how many trees are identical. The answer is going to be 0 through 8. Like, it has to be some number between 0 and 8. Let's start solving it. I wish you could timestamp like that. That'd be so cool. So what do we need to do? 3. Evan says 3. Evan, if you're right, you get 1,000,000. We'll see who gets it right. Take your bets now. I'm going to figure out the answer. We have 8, 4, 2, 9, 6, 3, 0. We're going to subtract from that the standard deviation, which is our uncertainty. Standard deviation is just a measure of variation. It's like saying, well, we could be off by about this much. And I think David's right. I think it's 8. I think it's all 8, because that's 83.1, and they're all above that. So David, 1,000,000 points right there. You are right, David. They're all basically the same. And they're all basically the same. What you're looking at, I'm going to hit my microphone right there. What you're looking at is, sorry guys, you're looking at all these trees basically in here. And that's, I think, why we plotted that out. They're all basically identical. And actually, we would see 83.1 is going to go about there. So, yeah, sure. So what we do, great question, Ivy, 100,000 points. Let's zoom back in on this. Woo! So we've got the numbers on the slide, and we are going to take the accuracy. So everyone see this accuracy right here of the best model. So we take the accuracy of the best model. So I'm just typing in the accuracy of the best model. And then I'm going to subtract from it the standard deviation of that accuracy, which is our uncertainty in it. What we mean by standard deviation is, well, I could be off by about this much. It's like, well, here's what the estimate is, and I could be off by about this much. So all we do is take the estimate, subtract the standard deviation, and that gives us a guideline for about like, well, our accuracy could be about this low. It's kind of like, for any of my Stat 200s, making a 68% confidence interval in the lower bound of it. So this is identical to doing a 60, well, virtually identical to doing a 68% confidence interval's lower bound, because you're just going one standard deviation below the accuracy. So we always try to relate concepts to things we've maybe learned in other classes. So, and I was going to show you guys, I'm wearing some Kingsport carousel today. So I got some Kingsport pride going on right here. So when everything starts back up, go visit the Kingsport Carousel, and you can hear, "Welcome to the Kingsport Carousel. This is a 3.5-minute ride. Please do not exit the carousel at any point, unless there's an emergency." I didn't say that. Here's the importance. What makes good wine? Welcome to class. What makes good wine? So, but how the way alcohol makes good wine, we don't know. And is it just by chance that the best accuracy? Yes, that was pure by chance. That's just the standard deviation on the accuracy will just be calculated for each individual accuracy, and it being the lowest would mean it would have the least amount of uncertainty, and that was just chance. So we see what plays importance in wines and the variables we've chosen. It's alcohol, it's density, it's chlorids. We can start to look at the tree. What's your favorite wine? I like Riesling. Riesling's good. I'm over 21. I can answer that question. Riesling is good, or dessert wine. Like, if you were to give me some like cheesecake and dessert wine, that sounds excellent. So, like, what is it? Like a late harvest Vignol or something like that. Like, that'd be really good. We got some Pinot Noir here. So, says, you know, that's maybe how it's pronounced. A red wine with steak is excellent. You guys are gonna make me start thinking about food and steak and all that good stuff right here. 14 hands. So we got all these distance. Oh, so good to see you, Carson. Carson, we were literally just talking about, hey, Carson, question for you. 1,000,000 points, Carson, if you're still here. How many standard deviations would we go out to make a 68% confidence roll? How many standard deviations would we go out to make a 68% confidence roll? So we're actually doing that in class right now, and everyone is voting red wine with steak right now. We're making a 68% confidence roll right now. Carson might have already left. And so good to see you. The answer is 1. Carson can still get those points for popping in as long as he says it. Let's see. But we just go out 1 standard deviation. So these concepts relate, as I was just saying a moment ago. Carson, you are right. Is it that... you only need to tell me once. Is that we're just going out 1 standard deviation. Oh, you're fine, Carson. We're only going out 1 standard deviation. And it goes back to Stat 201 that in this class, we're just going out 1 standard deviation to make a very small confidence interval to see if things are basically identical. Because if something is within the 68% confidence interval, we're like, okay, well, these things are virtually identical. And as we just saw, all of these accuracies are within 1 standard deviation of the accuracy of the best. So all we do is take our estimate and go plus or minus 1 standard deviation, and we were within 1 standard deviation of the best, and that's basically doing a 68% confidence interval, which we do in Stat 201. So we use all these concepts throughout statistics that we learn at the base of it. We can use the part model to fit a tree and study it. Let's look at the CP value of it. So let's, text is so small, 2 seconds here. Let's zoom in on this. Let's do this. Okay, cool. So we've got here alcohol. Is the alcohol greater than 11? Yes, let's go to the right. This is very alcoholic wine. And then we want to look at the sulfur. And once again, what what do we have going on right here as the tree goes within and looks at a variable within another variable? Good seeing you, Carson. See you later today. What do we have right here as a tree goes within one variable and looks at how another variable impacts that variable within another variable? What is it for 1,000,000 points? That is controlling for what, which is very important that trees do. We should know this, like, boom, trees control for this. They already handle this perfectly fine. And thank you for those Twitch subs. I think we literally got some Twitch subs. What do trees control for? By looking at a variable's impact within another variable. Like, okay, so for these high alcohol wines above 11, interactions, Christian got the million right there. You are right. This is controlling for interactions right here. And it's how does free sulfur dioxide impact? Awesome, awesome, Connor. Yeah, I saw you right there. Don Morrow, and we got Smooth Service have both subbed. So thank you for those Twitch subs. I need to put in the next chat and be like, hey, sub to the Twitch channel if you want. We're going to start, we're going to put office hours to it, Connor. One link, you come to it, it works. So thank you, David. So cool. And so you'll get the thing when Stats 1 goes live. So I might start doing just random office hours. But I want the first time we do it to hopefully get a good audience, and let's try to build that Twitch channel. So here we go right here. This is a very, 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 very important command we're using. The post resample command right here is just going to do the predictions on the holdout to see how it's doing, and we can compare these models. So interestingly enough, and I do love the way we do the slides, the best model was the k nearest neighbors, but this model is actually seeing how it predicts on the holdout. This is key. And once again, you can always copy paste these commands or these functions, I guess commands, functions. You can take it and use it, especially for your take home. This is going to be huge. So you should take a note right now. What does the post resample function do? Well, we need to take from it two things. We need our predictions using our models. This is doing the predict function on our model and taking the new data. So we're taking new data here to make predictions on. So we're predicting using the k nearest neighbor on new data. These are all basically blank blanks, 1,000,000 points. These are all basically blank blanks. Like, you have to give it these. So this goes literally back to 201. I wish, Carson, you still get 1,000,000 points if you get the answer. Yep. So, you guys if you go back and look at the videos, you can see the timestamps in the chat and then timestamp from that. Amazing idea, Ivy. 1,000,000 points, Ivy. And I know other people were doing it, but you clued me in on it. So what does this code mean? So, and make sure to go back. Remember, these need to be in the comments down below the video. At the end, it needs to be in the comments. So, like, you'll actually type the time in and then do that. What is that code going to predict for you? 1,000,000 points. It's going to give you blank blank. Not X something. It's going to give you this right here. It's the predicted value of this. What is it in notation? It's going to give you blank blank. Does anyone know? I've stumped everyone. I might have to give away the answer. It's going to give you Y hat. Y hat. I know everyone's following along, so if I stump you guys, I'll usually give away the answer when I see everyone's following along and answering. Y hat. Y bar would be the mean of the Y variable, and Y hat would be predicted value of Y. Okay, so still 1,000,000 points. Second question, what is this going to give you? What is that going to give you? This is Y hat, and what's the other one going to give you? That is from the holdout, the actual quality of the holdout. 100,000 points, Aaron and David right there. What is the actual value of the holdout quality? What is that right there? Who knows? 1,000,000 points on the line. The other one is Y hat because it's the predicted value of Y. And so think about residuals and stuff like that. If you know how the formula for residual equals actual minus predicted. Who knows? Not Y bar, because Y bar would be the mean of the Y. So that won't give you Y bar. Everyone's saying Y bar in the chat. Not Y bar. It'll be... I'll give you guys like 10 seconds. Not X hat. We won't predict X because we'll only do predictions on the Y variable. Still 100,000 points, Tyler. So we only predict on the Y variable. We make predictions for the Y. It won't give you the mean of the X because remember, we're predicting quality, so it has to be a Y. So what is that in notation? Think about residuals. Everyone's answering 100,000 points for all these answers. It'll be some sort of Y variable. And think if we do actual minus predicted, all it is, I'm going to give it away in 5, 4, 3, not this close. That's kind of what's going on right here. Now remember, it's not sums of squared error because it is categorical. I see where everyone's going with this, but this is just the Y values. I wish I could write on these slides, but this is just the value of Y. This is the Y value because it's the actual quality in the holdout. So that's the Y values of the holdout, and this is the Y hats for the holdout. So all you're doing is the actual and the predicted, and you're kind of doing an accuracy type thing. Don't worry, all those guesses, no one got it right. Everyone who took a guess, you only get 1,000,000 points for your guess, but I really appreciate those guesses. Don't worry, it's how we learn, it's how we remember things. So this post-resample function will take for us the predicted value, and it will take the actual value on the holdout. So we have a predicted value on the holdout and an actual value in the holdout, and the notation for that is Y hat for predicted and Y for actual. So it's just going to tell us the accuracy using those two arguments in the function. So don't worry, you guys did excellent. We're almost to the last bit of the lecture today, doing excellently here. And we will record some lab stuff on Friday. So sorry, I know there's a lot going on. Do you guys like the recorded lab? Does it help you solve it? I'll be solving all the code through it. So you will get a recorded version of this lab. I think that's the best thing we can do. Like, do as much time with the slides as we can and then record a version of the lab. As long as you guys are liking that style right there. And I might do the recorded labs on YouTube, because that way they're easier videos. So, but then we'll do stat lab on everything else. Yeah, that helps a lot. Awesome, Jessica. I want you guys to keep telling me what you think. We're going to keep augmenting. And then I'm so busy tomorrow. We might do it live tomorrow. Especially maybe I'll do it like as a night stream because night shift people. So fiance's working night shift. So so I don't know. I won't be doing much at night then after 8 p.m. or so. Faster to develop on larger data frames. So here's the pros and cons. Go back and review this slide. It looks into interactions, naturally incorporates complex interactions. This is everything we've been saying. Not too sensitive to outliers, and we'll be doing it. I'll find a time tomorrow to do it. Here's the key drawbacks. If Y is numeric, still have to figure out exactly what to predict. Do we use transformed values? All these different things right here. Often don't predict well as regression models. Well, we'll just compare it. Usually overfits. Well, we'll try to, not have that happen. No test of significance about predictors means no p-value. So you can't say what's the most significance, even though we get the importance. Relatively high variance. So each tree can be vastly different, and we can't really interpret it well. It's much harder to interpret a partition model, and it's going to get way harder here in a moment to interpret them. All tree-based models have predispositions to create rules using variables that have more unique values. Yes. So I'm going to show you something right here. We're going to have to go way back. Here we are right here. Does everyone see that ACT, let's zoom in on it, ACT has a more kind of like sharp features to it. That's because there's less unique values of ACT, and over here, high school GPA, which is what the variable is. Sorry, this text is so small. High school GPA has way more unique values, and thus the tree has more opportunities to split. So the tree is literally going to look through every X variable at every X value, unique X value, at every split. It does tons of calculations, but the variables that have more variation in them and more unique values are going to be the ones that split more. So it was more likely we would split on high school GPA because it's got more unique values, and then you can get these weird things where you get this sudden divot up and down around it. So the unique values can lead to more unique splits or more splits in the tree, and you see that right there, which is in the notes way over here. We're going to go all the way to the end of this, examples of pros and cons, right here. We're all the way, and then that's basically it. So discretization, yeah. So discretization is a very important thing which we cover near the end of the class. Discretization means to make a variable discrete. So we can take a variable that is numeric and turn it into a discrete variable, such as we have like 0 to 5, 5 to 10. And what is that going to do to the unique values if I take something like age and turn it into age groups? Age groups, for you to remember right here, is a discretization of age. If you have someone's age, like I'm 38, if you have someone's age and you discretize it to say 30 to 39-year-olds, what's that going to do to the unique levels of age? What's that going to do to the unique levels of age when you discretize age? Any ideas? Million points, secret million points. You know what time it is. My stat winners know it and they love it. It is that random million of the day. What will it do when we discretize it? Going from age to age groups, what will that do to this right here? Going from age to age groups will do this to the unique levels. What will it do? It's going to reduce the number of unique levels. David, you are completely correct. Amazing answer. You typed it out nice and perfectly. It's going to reduce the numbers of unique levels, which would mean we're probably less likely to split on that variable because it doesn't have as much unique levels to split on. David, amazing answer. Great job. So we can do what's called discretization to turn something into a categorical variable. Nicholas, I'm throwing you the million also. Love that you answered in right there, Cole. So bagging and random forests. Awesome stuff. What I love about this is how recent this is. This is so recent because you look at things like perceptrons in neural nets. People made up these things early on, and then they were like, well, you know, it's cool, but we can't do it because computers don't have enough power. Computers weren't fast enough, weren't quick enough, weren't powerful enough to do all these amazing things. And it's only in recent years that we can literally be doing all these crazy things with statistics because we got super powerful computers. And even then we can push them to the limit. I mean, you look at Oak Ridge, they've got, you know, what is it, Titan, or I don't know, all these Summit. I think it's Summit right now. And they're constantly making their computer better and better and better and better and better. And it's just so powerful. Summit, that's awesome. 100,000 points right there. Spencer confirming it is Summit. And so I want everyone to guess what time it is. Oh, too bad. You see, I said that and I looked at the clock right then. So if everyone were to guess what time it is, then we could use everyone's guesses to actually... It's not fair when we're all in front of the computer, right? David did it right as it turned to 1:34. But if we were to all guess without looking, I probably would have guessed about 1:30 because I look at the time too much lately to kind of know like how much time do we have left when we're teaching. But I literally like glanced at it right as I said, I was like, oh, I've cheated too. So if we were to be in a classroom with Tyler, 100,000 points, Tyler. If we were to be in a room with no clock, Tyler's such a great guess. So if we were to be in a room with no clock and everyone were to take a guess, you know what we'd actually see? 201 stuff. I'd love it if Carson was still here, because guess what? We'd see something close to the normal model right here, where people would be off by kind of a plus or minus amount. And so what we see is this idea of taking multiple guesses is a better way than just using one guess. So guess what's better than a tree? Who has any idea what's probably going to be better than a tree? Any idea of what's probably better than a tree? A forest. Like, amazing. Why not use a bunch of trees instead of using just, yeah, Saeed, 100,000 points right there. Why not use a bunch of trees instead of just one tree? So we can do this all the time right here. This is just an example showing you a bunch of guesses. They're all averaged together, and we can see the standard deviations on it, all this good stuff. We're just averaging multiple guesses still going on, and we can look at the typical error. So here we go right here, and I believe we've started making trees. Have we started making trees? Let's look at the code. So we go right here. I'm skimming through a few of the examples, and this is why the shorter slides have less examples, but this is still just doing a bunch of averages, and let's start looking at the tree. Here we go. Okay. Random forests. Build a collection of partition models which are as independently uncorrelated as possible and take advantage of all of the predictions. We also have what is called ensembling. Ensembling is taking different models right here. Like you could take a k-nearest neighbors model, you could take a naive model, naive Bayes model, you could take a logistic model, you could take a partition, you could take a neural net, you could take a support vector machine. You can take a bunch of different models and then ensemble them together. So you're hoping that all these models right here can work together to make one model. So that is called model ensembling, which we're not doing today, but it's still the same idea that if you had a bunch of trees working together, that's kind of an ensembled model by making a forest. So I would say technically a forest is an ensembling of trees. I think that's a pretty good way to state it. A forest is an ensembling of trees. It's just putting a whole bunch of models together to work together. All these models are going to do their own work and then come together to make final predictions right here. Sarah says we discussed it in our tour later on. So we've got right here, partition models suffer from high variance. What does high variance mean? If they had different data, they'd work completely differently. And what we see right here is, especially the original split, I should say. Here it is right here. We built it on, yeah. So think about this. when you build your tree, that first split dictates every other split within it. So when your data kind of dictates that first split, then it's going to drastically alter where it goes. So what if we had split on a different variable? Every split is now going to be contained within a totally different variable also. Does everyone understand what I'm saying? Hopefully I didn't say it too convolutedly, but that first split is dictated by the data. Something that is dictated by the data means high variance. So the data controlling our tree to a high degree means it's high variance. We don't want that. We want it to work the same from each data set to each data set. So we've got this high variance model because when the tree splits, it's controlled by the data, and even that first split is going to control every split within there. So if we have a high variance model, we could have high generalization error. So what do? We are going to let multiple trees work together. Now, what's funny is it's like, well, everyone makes bad predictions, but if we average together these bad predictions, we'll get a good prediction because it's going to take the ones that are a little off here and a little off here and average them together. So our goal is to take all these high variance trees and put them into a forest to work together. Here we go with bagging right here. It's important to know exactly what bagging is. Bagging refers to the ability on bootstrapped versions of the training set. So what is a bootstrapped version of the training data right here? So here we go. It's got the instructions here, but I'm going to go into a Word document and tell you how it works. Have I explained this already this semester? Have I explained bootstrap samples? Let's get some yes or no's in the class. Who knows what a bootstrap sample is? I know I've explained it during office hours. I think Connor's heard me explain it. Awesome. Then we're going to do it a little bit quickly, but let's explain it. A bootstrap sample, which is bagging. So briefly, so let's review it. If we have the numbers 1, 2, 3, 4, and 5, I want someone to make a bootstrap sample of this. First person, million points to tell me a bootstrap sample of this. A bootstrap sample of 5 of this. Someone give me a bootstrap sample of 5. Should be David, million points right there. You basically gave the definition of it. Amazing. That means I taught it well. I should million points, Brian. So, oh yes. Oh, be careful, Will. Will is correct. I'm still giving it to Will. But remember, Will, with bootstrapping, Ivy, remember only 5 observations, but still million points. I love Aaron's answer. Aaron's answer is 5, 5, 5, 5, 5. That is a bootstrap resample of this. So bootstrap resampling allows for replacement. So all these answers you're seeing in the chat right now are bootstrap resamples. Make sure to use 5 observations, but because I think there's a 6. Maybe you just type 1 to 2. Still million points, Ivy, there. These are bootstrap resamples, and technically you could get in a bootstrap resample, you could get 2, 1, 3, 5, 4. You could get 1, 2, 3, 4, 5 again. And this is what it is think about this. If we make a model from this bootstrap resample right here, this is a different data set than this bootstrap resample. So this is boot 1, and this is boot 2. And then each of the trees gets a different set of data to create the tree. Does that make sense right there, Kyle? Each tree makes its splits and decisions based on different data. So every tree has a different set of data that creates the tree, and thus you'll see different things happen because different data will create each tree. So the first tree is going to be made from the bootstrap sample 1, and the second tree is going to be made from bootstrap sample 2. And so we see this right here that we get different sorts of data making different trees, and so you'll get different trees. It really just helps making different trees. Does that make sense, Kyle? It's like different data leads to different trees. It's still our training data, but so essentially provides a better, not better trees, just different trees. And then the trees will work together to make a better forest. So they could, and they will be the same number. So, and then Ivy, but they could be the same. No, they can be the same number. Yep. Like 1 and 1 is the same right here. They can be the same. They can be different. It's sampling with replacement to make a new bootstrap sample. That's what a bootstrap sample is, also called bagging. Bootstrap samples are sampling with replacement. So always make sure you can make like a bootstrap sample from that, and that would be a bootstrap sample of that data. Even though the first one has all the values in it, that can happen with sampling with replacement, and the second one can happen also. You can get the same values again. Does that make sense right there, Ivy and Kyle, for both those? Timestrap, bootstrap samples explained. So you can get the same observation again. Make sure to put them in the comments. You can put 2 of them. Put the timestamp. You'll type in something like, I wonder what will happen if I do this. You'll type in something like 30:45, and then that'll put a timestamp in the video. Like you'll do it as a comment. So tons of bootstrap samples right here. So we have right here, they contain some of the same values. They hope that they're independent enough. Yep, it's all what I explained. So when we do this right here, we've got right here that about 1/3 when we do this in the bootstrap samples are actually used for the training right here. About 1/3 of the individuals from the original training data will not be used representing the bootstrap channel. We refer to them as out of the bag, and then 2/3 will be used in the bag. So the way the algorithm does it when it makes it, it uses about 2/3, 1/3. There's ways to do this and control this. The same individual in training set can appear more than once, will appear. Yeah, if you use a large enough data set, it's almost will. It's like will with like a star next to it. So we get right here, that's what's going on. So the bagging procedure also yields an estimate of generalization error without having to run k-fold cross-validation. That's why it's holding out a certain amount of data right there. It's using the predictions to make it. Consider making a prediction for the individuals in the first row. Find all the bootstrap train data, predict the y values, repeat this individual, yada, yada, yada. This out of the bag error estimate is a reasonable estimate. So literally this right here, let's take a huge note right here. You ready? We will not have to do this. But why is this being done? Why is this being done for us right here? It's to figure out our what. Why is this being done for us? Any ideas? It's to figure out the estimated what, which it's basically taking place of, as the slide just said. It's basically taking place of this. It's to figure out the estimated, who knows it for a million points, to figure out the estimated what. Kind of, no, not the holdout, because remember, close, million points those answers still. We're throwing crazy points today. So if we see right here, it's not going to be, we have right here, because we need to see how it actually, estimated generalization. David, you were right. So what it's going to do right here is it's going to make the training data set, and it's an estimated error. So error estimate is reasonable estimate of the generalization error. So it's an estimate of the generalization error on the model. But remember, when you see the estimate of the generalization error, that means it's actually the what. I want to see it again for a million points in the chat. And once again, it's taking place of the k-fold cross-validation, and that's a huge thing right there. You should automatically clue in on that this is taking place of the k-fold cross-validation. So this is not the holdout error, it's the what. Because this is going to help us pick our model. It's the estimated generalization error, the validation data. Boom, you got it right there, David. Million points and 100,000, or yeah, I don't know. It's going crazy with points today. Remember to put these points in your sheet. Keep track of them. Be like, you're looking crazy points right now. So we've got right here variable importance. Just variable importance tells us which variables are most important for a particular bootstrap training set. Count up the reduction in the Gini index for splits, which use the predictors. Average together these numbers are over each bootstrap training state and call it the mean decrease in Gini. Not too important right there. And here we get to random forest. Our last big topic. So random forest is going to be a bagged tree. Now a bagged tree is going to take into account different X's in the tree. So we just saw what bootstrap trees are. And then we're going to look at bagged trees right here. So we're going to take an additional modification, as the slide says, and we're going to put in something extra right here. Now, all that we need to know is two things. Bagged trees are only going to take a subset of predictors. So a random forest here, when we have bagged trees, are going to take a subset of predictors, as in a subset of X's. So they're not going to take all of the X's. Does that make sense? So remember how we said when we make trees, the first split kind of dictates the tree? Well, now if we have this really good variable like alcohol, is there a chance that alcohol might not be in our tree with this? Is there an example that alcohol might not be in our tree? Is that possible? Possible, yeah. So, well, and this isn't the 2/3. There's a lot of ways to compute this right here. Usually P over this. If P is the number of predictors, usually take about right there, we take about that many predictors. So if there's 30 predictors, we might take 10 of them. Or if there's 30 predictors, we might take like 5 or 6. There's different ways of doing it. So we don't have to memorize like how many predictors will we take. So the big thing to know is that we're not taking all of our X's. So in every tree will not always have alcohol in it, because that's one of the really good variables. Alcohol was such an important variable, but every tree will not have alcohol in it. Every tree will also, if we're using bagging right here, so if we're using this right here, every tree will not also have every observation, and we're going to grow every tree to the maximum. I know this seems crazy. When we grow a tree to the maximum, you might think we're doing this to the tree. If we grow a tree to the maximum, we'd probably be whatting the tree. You would think we'd just be overfitting it. It would have a bad generalization. But remember, we're going to take all these trees. David, you got it for 100,000 right there. We're going to take all these trees and average together their predictions, and we're going to put everything through each tree and see where it would go. So every tree is going to be used to make predictions for every row, and then we're going to take all of these predictions and average together all these predictions. Could you imagine doing this by hand? Like we're going to grow every tree from random X's from random rows that have been bootstrapped sampled, and then we're going to grow every tree to the maximum and then use all of those predictions for every observation through every tree and average those up to make a prediction. It's an insane amount of work, but you have to do it in steps. Exactly. You have to do it in steps. You have to be like, okay, we are going to use right here bagging, which is basically bootstrapping. Bagging is bootstrapping. And then we're going to go here and we're going to use random forest techniques to take just random X's, about 1/3 of them, or, about, it could be square root of P predictors. We don't have to worry too much, but we're not going to take all the X's. That's the biggest thing to know. And then we're going to grow every tree to the maximum. And all these trees are going to vote. Each tree is horribly overfit. The trees fit the bootstrap data training perfectly, because think about this. Each tree is going to be grown to the maximum, so it's going to be so overfit that it's going to get everything perfect. If the random selection of predictors contain none that have any information about Y, then adding a rule based on them is likely to fit noise. It's not good right here. The predictions are always more accurate and quite often by a substantial amount. So usually, think about this. This is saying down here. When we average together all the predictions from the trees, as I was saying, that's what we do. We take all these trees, all these overfit trees, and we average them together. Usually a forest will do better than trees. It's like almost always. I can't imagine. I think I've seen it where it doesn't do better, but it's just that you got lucky on a tree probably. So trees can get lucky and be like, oh, this is a good tree. And you don't know it's going to work better. We have right here the number of trees. It's not plural. This is a tuning parameter. These are huge notes on what you need to put into your model. Tuning parameters right here. We've got here the mtry. This dictates how many predictors are picked at each random for each new tree. We're making numeric predictions. We've got right here 1/3. So all this right here is how many predictors it's going to try when it puts each new tree in there. So the mtry is directly related to, go back to it, mtry is going to be related to this right here. This is the mtry. Exactly. Great job. Make sure to put it in the notes at the end, the comments at the end. Thank you, David. So right here, mtry is how many predictors we're choosing, ntree is how many trees we're going to choose, and here's the code. We do have one more topic, which we'll start next class with, but I'm going to make sure we go thoroughly through this topic. You see right here, we've got different models being used. So we've got here, we're just making our training data, making our holdout. We've got right here the, are we predicting on accuracy or ROC? Million point question at the end of class. What are we doing? Accuracy or ROC prediction? Are we doing accuracy or ROC tuning, I should say? Accuracy, the answer is down below also, but accuracy, David, you're right. You can also tell down here that it was accuracy, but it doesn't have the two-factor, two-class summary on there. So we don't see that, so it's not there. Great job answering the chat. Class probs equals, no, this is only when this is here. When only this is here, this is going to be accuracy. When only this is here, two-class summary equals ROC. You are correct. Two-class summary equals ROC when you see that in the notes, or when you see that on your sheet. We've got here the accuracy of how it works on the forest with the parameter none. Accuracy here. Let's take a look. This is the logistic model, I believe, which has no parameters. Well, darn it. The logistic model beat everything out and by a good margin. Darn you, logistic model. And then we have here the R partition. And then here we have the R forest. And the R forest did better than the trees. So does everyone see right here? Let's put this right here. We've got the R forest right here, and it did better than the trees and most of these are better than the trees, but the logistic model did the best. That's just the way it can go sometimes. The logistic model did the best. And I think we'll come back here. I'm just going to mention briefly boosted trees, and we'll start next class with this. Boosted trees, woo! Boosted trees have a few more tuning parameters. So the first thing you're seeing right here is what's called the interaction depth. The interaction depth is going to control how large each tree grows. And so we've got that tuning parameter here. We've got our training data. And let's just take a look at boosting trees. We'll start next class with this. The learning rate is the shrinkage parameter, how fast it learns, fast or slow learning. And let's take a look at just this. I just want to show a few more slides. Oh, I never look at the kappa. Oh, was I looking at kappa? I don't like kappa. Was I looking at kappa? Oh my gosh. Oh my gosh, 1,000,000 points right there. I can't believe it. I was thinking about what I was going to be teaching next. Wow. No, David, that's a 5,000,000 point answer right there. David, I was just seeing if everyone was following along. You are correct. I think it's just because of the way I'm going to blame it on this right here, which I think was grabbing kappa. I think I did. I think I grabbed this accuracy, and then I grabbed these accuracies, and then I grabbed the kappa just because the way it was written. David, 5,000,000 points, I mean it. That's a huge correction because reading the output wrong got me the wrong thing. Guess what works the best? It is the tree. David, thank you for following along. It's very easy to misread output. You can do everything correct, and then you can misread your output and get the answer wrong. So the accuracy is the best for the tree, and it looks to be way more than one standard deviation. Thank you, David, very much. The tree right here, or the forest, the forest has the best accuracy, and it's like by a mile. It's way higher than this in terms of standard deviations. So yeah, the forest was way better. Weird that the logistic model, I was like, logistic one. It's like, no, the forest one, and the trees did pretty horrible. No, he's following along very well right here. So you can see right here, you just notice how the number of trees, all this slide is trying to show you right here, and we'll probably end with this. I'll probably start next class with the next one. He just ate like all Snickers, just like was ready and raring to go. We've got right here just the error on the model as we increase the number of trees and the different methods being used. You'll notice what goes on right here. I know, great job. You'll notice that we kind of get diminishing return when we keep increasing the trees. So we get diminishing return because you would think it would keep going down. So I'm a big failure at this, that I keep making my trees more and more and more and more and more, but you get this diminishing return on your trees where you just don't get more out of your trees as you keep throwing in more trees. We will talk about boosted trees next time. Really the only thing to know, and there's number of trees growing again, same sort of idea, that as you put more and more trees into these, you get return, but you kind of reach this diminishing return. I mean, look at how good we go from 0 to 1,000, and as you put more and more into this, it's just like, well, you get less and less out of it. And XGBoost, oh my gosh, I will not make you memorize all the parameters due to XGBoost. We got regularization right here, all this good stuff. So I want to point out what you should know for the remaining slides, and we'll go back to it. It's just got examples to end. Once again, I use the long version of the slides, half pot of coffee. I should make some coffee. What I want to point out, take a note on this. This is our last note for class today because it is end of class time. The last note for class today is know your tuning parameters. Put that in the chat for 1,000,000 points. Everyone can put that in the chat for 1,000,000 points right now at the end of class. Know your tuning parameters. At least have a cheat sheet with them to know what they are and what they do. When I see interaction depth, I know it's right here. I know it says at the top of the slide, but I know what interaction depth is like that. It's how big each tree will grow. So when I see here an interaction depth of 1, interaction depth of 3, all these things right here, interaction depth of 2, it just means how many times the tree splits. You have to know your tuning parameters. You have to know what interaction depth is. You have to know what min observation is, which I don't think min obs is here, but min obs should be. Where's our min obs right here? N min obs in node. So min observations right there. Like what does n min obs mean right here? This is the number of minimum observations in each node. It's like when you get down to the bottom, Matthew, good to see you. Let's add Matthew right here. Shrinkage is how quickly the tree learns, and number of trees is number of trees. Remember, and this one's plural. Why you do that to us, GBM, but you need to know your tuning parameters. So n min observations in node stands for the number of minimum observations in a node. Interaction depth is how big each boosted tree will go. Shrinkage is how much it's learning from each tree, and n trees. And really, this is the main thing to know about boosted trees, just its tuning parameters. And then when you go to XGBoost, XGBoost stands for extreme gradient boosting. So XGBoost is extreme gradient boosting, and it puts regularization in here. We'll talk about this more next time, but it has all of these tuning parameters. So I want you guys to think about what we started off class today with. This is my last 1 minute rant. Don't worry, we'll talk about this next time too. But think about this. How many models might you be making? Do you look at this? This is like tuning parameter 1, tuning parameter 2, tuning parameter 3, tuning parameter 4. If you were to use all of these tuning parameters right here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, if they were to have 4 levels, 5 million point question in class, I know it's over, but if there would be 4 levels to each of these, then how many tuning parameter or how many models would you be making? If there are 4 levels to each of these, which you can do way more than 4. If there were 4 levels to each of these, how many for 5 million points, how many different models would you be making? If there were 4 levels to each of these tuning parameters, which are just, you're going to be like, let's make them all with this, 4 levels to each of these. And I think there's 10 total. Who knows it in the chat? Is that the answer? I got to find out. If I do that, then I'm going to show the answer. David, I think I know how you found it. Yeah, you both got it. Yep, that's it. You understand the concept really well then. Let's end class with that. David, amazing work. Was it you who had the Wheaties? Yes. I'm going to give 1,000,000 points to everyone else giving the answer right there. Ivy and Evan, great job. And David got the 5 mil. Huge points on that. You understand the throwback concept that tuning parameters are the different sorts of models we are making. And the more Wheaties, I need to get some Wheaties. Eat your Wheaties before the test. David, amazing work today. And everyone else too. But you understood the throwback question right there on how we use tuning parameters to increase the number of trees. And tuning parameters are not number of trees, number of models. And tuning parameters are just things we're going to adjust to make different models. Those are great. Awesome. Christian's looking at his points right there. I'm going to try to get the points to work better, Christian, because I swear people should have more than 80. And I think it's an uppercase P right there. I think it is. So put the uppercase P, check your points. We'll head out here. I'll take any questions. There's 9. Connor might get 5 million points also. 1, 2, 3, 4, 5, 6, 7, 8, 9. Connor, 5 million points. Correction from Connor. Slide 71. Yeah, let's do that. Slide 71 right here. Cool. This is going to be the how our models did. So all we're doing right here, the code at the top, the tree best tune, is going to be the best tree out of all this. It just gets you the tree that was the best. So this is the one that worked the best on the validation. We have not tested it on the holdout yet, but this is how we estimate it'll work. But once again, this is the CP of it. So if you actually use that to make your tree, great job. And I'll keep working on these mu bucks to have people get more and more mu bucks. So hopefully it's working properly, but I'm working on it. So we have right here the CP, which tells us how big that tree is going to grow. So you could go down here to this output to see the CP of the tree. And this is going to tell us the CP used to make the tree, because the CP controls, yep, that would be it right there, Caleb. Caleb, 1,000,000 points, great answer. This would be the CP, which controls the growth of the tree. And then the accuracy and the standard deviation of the accuracy are the main things we need to clue in on. The accuracy is how well it predicted on the validation. Make sure you know that this is not how it's working on a holdout, it's the validation on it. So we're using this to see how well it works on the validation. Hence why we're picking it. We pick based on the validation. We make our model on the training, and then we see how it does on a validation, because that estimates how it'll do on new data. So this is the estimated accuracy on new data, known as the validation. And then we have right here the uncertainty in that estimate. And then we use that to figure out if any other model is similar. Visualizing that, once again, we found 83.1. So we go back to the visual on this, and we see that 83.1 is about here. And every model within this range, if my mouse would stop jumping, every model within this range is probably pretty similar to each other. I use the standard deviation to figure this out, because one standard deviation is about, not that much. It'd be like someone who is like 6 feet tall being like, I'm so much taller than you. You're 5'10". You'd be like, we're about one standard deviation apart. That's not that big of a difference. But if these models have a big difference, which you can see between like these models down here, these models are drastically different, because that'd be like 6 foot tall and 5 foot tall. They're drastically different when you get out of that range between the models. Does that make more sense right there? Herman, who asked it. If that makes more sense, we're probably good to go. I'm going to hop off, probably get some more water. And Christian right there. Does that make more sense, Christian, right there? On how we interpret the accuracy and the CPs we would use. CPs tell us how big the tree grows, and smaller CP means larger tree, larger CP means smaller tree, and yep. Awesome. I'm going to head off. That's got it. Let's see if the buttons are working again. Oh, I don't know why. I got to reconnect the stream deck. We'll work on that later. Okay, talk to everyone later. See you next class.